let's go on with E and M part 5. Of course, we're going to start with the last time. Last time on electricity and magnetism discussion, we talked about work and energy associated with electric charges and fields, right? We talked about work as something very specific. And do you remember what it was? I'll write a more complicated one where we have the sum over all of the charges of Qi and multiplied by the potential of I. And I said that this kind of manifested itself in a very unique way. So I'm going to do them kind of backwards because I'm working here with this idea on the fly. But like if you had a bunch of charges, Q1, Q2, and then you just list it out, and you have two, we're going to consider basically two charges, Qi and Qj. That was the premise. And we could figure everything out so that we could find the potential really in regards to the whole system by considering just a single charge like Qi and then adding all of the charges to it one at a time. Anyways, so work in this smaller version is really just, going to be the charge times the potential, right? And we said that there was something kind of specific about this potential, or about this formula, right? Or about this work, more or less, right? The work disguises itself in an intro class, if you take an intro electricity magnetism class, as U, which is usually something like Q1, Q2 over 4 pi epsilon naught times R, inversely proportional. And that was kind of like KQ1, Q2 over R, right? And that was potential energy. That's how potential energy is treated. But really, this is kind of the same thing, right? Where the potential is just equal to the one charge, and you just talk about it as if it's a potential associated with a single charge. Now, what else do we do? Oh yeah, we talked about work. I want to kind of remind you about the integrals over infinity, right? We talked about splitting the work integral up into two sections. We did this using some integration by part tricks that we talked about last week, where we were able to take the second term, which is the surface integral of the potential times the electric field, dotted with the infinitesimally small area, and we could take this and consider the region of all space. And when we considered the region of all space, this integral remained with a value, and this integral went to 0. So we were able to rewrite the work equation as just epsilon sub naught over 2 times the integral over some volume of E squared times d tau. Okay? Now, a few remarks about what we talked about last week. This is the new content, or the new discussion subject material or whatever. A few remarks that we did not talk about. So remember sign convention. Sign convention, signs like were done by convention, right? That's kind of the point. So we talked about bringing in signs. We talked about, a system with energy. How does it get this energy? Well, this energy is associated, like we could say, that we chose positive because the negative was what we used to make the system, right? Where did it go? I wanted to put the thing on my wrist after all, or arm. Now I can't seem to find it. I had it. I had it yesterday, I think. Now I can't even find it. So yeah, so anyways, the point is if we want to talk about where the signs of the energy came from, we can talk about the fact that the energy is necessary by building the system, right? Fabricating the system is where we get the energy from. So taking it away is you just pick one to be plus and one to be minus. Minus, plus, no, stop. Stop. Okay, how about where is energy?
I think I need to redeem push-ups to get you in shape.
If you guys redeem push-ups, just keep track of them. I'll do them after we're done. So, hi, Kibit. Good to see you. How are you? I am doing quite well. Good to see you. Been a while. Yeah, so energy is located where in this electric field? That's what I just told you. What is this work? This work is disguised as potential or as energy. And where is that energy located? Well, it's located in the electric field. I mean, that's kind of the point of it. Now, there's some subtleties with that. Like in electrostatics, you can kind of get away with the electric field located at the energy, located at the charges, just again, kind of by the derivation of the just by the derivation of the the way that you derive it is what I was trying to get at. So how about this? The last time I kind of mentioned superposition, and I was a little bit waffling, so let me be pretty clear about this and kind of clear up any confusion I had last week, because I could clear it up in my own eyes. Here's the thing. Work does not follow superposition for work does not follow superposition for multiple electric fields. Okay? Why does it not follow the laws of superposition for multiple electric fields? Well, let me show you. It's relatively simple. The idea is that there's going to be cross terms. The idea is there's going to be cross terms, right? The work total that we talked about last week that I was waffling on is because when you're doing an integration over a continuous charge, it's a little bit different than superposition. And that's why I said that it might not be the right word to use, even though I used it. That the superposition of the work is a little bit different when you're integrating over a charged distribution, right? When we're talking about superposition of energy or of electric fields, then this is what we're going to have to consider. We'll have, our E squared d tau, that's what we just wrote down, but what if we have multiple electric fields? Electric fields do follow the laws of superposition. So if we add up two electric fields, we do have to square them still, just like you would if there was a single electric field. But now notice that this is not a vector because we've dotted it. So when we do dot the two electric fields, we're going to end up getting some cross terms. Namely, we'll get the integral, and then we'll get E1 squared, not a vector, plus E2 squared, not a vector, plus the dot product of E1 dot E2. And this is all d tau. And then lastly, we can rewrite this as now, since this is D1 that looks like that, that's E2 that looks like this. We get this work 1 plus work 2, which kind of looks like a superposition, except we do have to consider the cross terms as well from this E1 dotted with E2 times d tau. And that's why it doesn't follow the laws of superposition. Okay, so where are we at now? Oh, yes, conductors. Now, okay. When I learned this, I had a big problem with how this was explained. So let me do my best to explain it the way that I was able to understand it. You have heard many times that the electric field inside of a conductor is 0. And you hear about it, why, but really I want to explain to you a certain idea about that. And namely it is that yes, the electric field inside the conductor is 0, but what they mean by that is the net electric field inside of a conductor is 0. Okay, there is electric field inside of a conductor. There's in fact multiple electric fields inside of a conductor, and they are set up in a way very specifically to cancel. So what is a conductor? So Griffiths gives two definitions, one insulator, one conductor. And the insulator is an electron on a leash. That's what he calls an insulator. I think that's very funny because, electrons, they can't do anything. They're on a leash. That leash is called, I think, potential is what keeps them where they're supposed to be. And a conductor is different because one or more of the electrons per atom are free to roam. Okay? That means that for a perfect conductor, contains unlimited amount of free charges. Charges can come and go as they want. There's nothing then keeping them down. So if we have just a bunch of free charges in here, so we're just going to have a bunch of free charges. Look at them. They're everywhere. And this is a neutral object without any charge. And this is what's really nice about this, right? So the electric field comes through. Now, yes, the electric field is going to come over. We got some different colored chalk. Actually, it's going to be perpendicular to the surface. So let's try to do that a little cleaner, I guess. And it's not that it's going to go to 0. It actually goes through the inside of the conductor, okay? And then continues on its merry way. Okay? Now, here's the thing, is once the electric field goes through and you have these charges inside that can move, what you get is an arrangement of charges on the, what do I have? Oh, let's do green, I guess, for that. Oh, I need something a little bit brighter. Let's do purple. Yes, purple looks good. So now what's going to happen is you're going to have a bunch of charges ride on this electric field. So you'll get a bunch of minus, if the electric field is going this way, you'll get a bunch of minus charges form on this surface, and a bunch of plus charges form on this surface. Okay, now the free electrons or the free charges are going to move in such a way so that very specifically, now you have an electric field inside. Did I do that right? I think it's correct. You have an electric field that goes backwards. I thought electrons go against. Yeah, electrons go against the and positive charges. Yes, there we go. And it always goes away from the positive charges. They're correct. Okay, cool. Now listen. The cool thing is you'll always get exactly enough charges on the surface here to cancel the electric field that's going through it. So the blue electric field is this external one that goes like this, and these charges are going to ride the electric field lines in the ways they want to. We always have the positives ride it with the electric fields and the negatives ride it against it. So the electrons or the negative charges are going to line up on this side of the conductor. The positive charges will line up on this side of the conductor, and then there's going to be a electric field going from plus to minus in such a way exactly that the E total is going to equal the electric field from the external and the electric field from the internal. From the induced charges is what we call them. Let's just do a white plus here, not to be confusing. Yes, so there we go. So that, okay, good, thank you. I thought so. I had it in my notes. It just slipped my mind for some reason. Okay. Excuse me. So the conductor does have a net electric field inside of 0, but it is from these induced charges that create a field in the opposite direction. Okay, so that is why we get what we get for this. Okay, and that's how conductors work specifically. Zandenhusk, thank you for the follow. Sorry if I said your name wrong. So then what do we have here? So there's a few things we should learn about this. Well, the first one is that inside of a conductor, the electric field is 0. So that's what we just talked about and why it is that way. Now, also, the next thing up is because of this fact, the charge density inside a conductor is 0. How do we know that? Well, we know that Maxwell's first equation from Gauss's law is the divergence of the electric field, which is equal to rho, the charge density, over epsilon naught. So if E equals 0, then rho equals 0. Okay. Easy breezy. Maybe it's a tautology because you get equal and opposite charges exactly the way the E fields cancel. So maybe it's a tautology. This is the way that I understood it. So I think that was important for me to figure that out, which I didn't get that from intro physics. It took me longer than that. Actually, the story is, Adrian, thank you for the follow as well. The story is that when I had to, wait, before you can start TAing, you have to meet in front of a board of teachers, and they have to, they give you some stuff to teach to them, right? And then they, explain, they go over whether or not they think you're fit to teach and whatnot. And they asked me about the electric field inside of a conductor, and at that point, when I was starting graduate school, I still didn't understand it. For some reason, I just did not have this intuition from when I learned it. It actually, after that meeting, I went home and I just figured it. I went home and I sat down and did it until I figured it out. Oh, I see. Maybe it is. Maybe it is the Kivia. Interesting. Yeah, so that's the idea. Interesting, Blayman. Yeah, I don't know. But that's the idea, is I didn't understand it when I was entering graduate school. I did understand it when I was entering graduate school, but it was the meeting to get into to start TAing where I realized that I really need to understand what's going on here in order to get me to finally sit down and hash it out. So let's see. Let's keep going with these. So we know that the charge density is 0, but where are the charges then? If they do exist, right? And there are charges that can exist, and they must exist on the surface. Charges exist on surface. So if there are net charges, they must exist on the surface of the conductor. The next up is The potential is not necessarily 0, but constant. That's one thing that I have a lot of students mistake, is that they say, oh, the electric field inside of a conductor is 0. Therefore, the electric field must be 0. But that is just simply not the case. What is the case? Well, it's either going to be, it has to be constant, right? And the constant might be 0 if there is no electric field on the outside and you just have a neutral conductor. But that's not necessarily the case. If what we do know is that if this is true, where the electric field dotted with any length is equal to 0 inside the conductor, that the voltage must be equal at any length, therefore it must be constant. There we are. So the voltage must be, the potential must be constant inside of a conductor since the electric field is 0. What else we got? Oh, there's one more. The E field must be perpendicular to the surface of a conductor. Let's just do perpendicular to surface. And we saw that a lot with Gauss's law when we were talking about charge distributions, and it's also true for this, that it has to be perpendicular in the outside of a conductor. Guess what? It's demonstration time. This is a fun demonstration where I can show you exactly how this works. Okay? Now, let me see if I can do this properly. And then we'll actually draw on the board and talk about how it works. Now what I'm going to do is I'm going to take this balloon.
Whatever you do, be careful with your delicate hands.
You are such a brat. Oh my goodness. Okay, so what I have here is I have 3 conductors. Okay, I have these are both made of metal, and then a tinfoil ball, and it's hanging on a string between them. Okay, now I have a balloon here. And what I can do is rub it against my head as such, right? And I will be placing charges, I want to say negative charges, on the surface of the balloon, okay? Now, this is a very, let's just get to it. So what's going to happen? Well, there's going to be charges on the surface of the balloon, and from the charges are going to be an electric field. So now we're going to have an electric field. Let's see if I got to put this in motion or else it's too heavy. It doesn't have enough inertia. So now as I add charges to this, if I put it close to this, then the electric field, I didn't knock it enough, and I think I just discharged the balloon. Hold on. Okay. It always takes me a few seconds to get this right. We'll get it. Hold on. So what's happening is I'm taking and putting electric charges on the balloon. When they're coming close to this conductor, the conductor is going to, separate the charges like I showed on, there it goes. Showed on the board. There we go. Now every time I go away from it, it's going to change, and every time I go towards it, it's going to change. And when I do this, the charges are going to be moving around in the conductor. Okay? And what happens is when this metal ball in the middle as a conductor gets close to the edge, it's going to take some of the charges. So now you're going to have positive charges on the one side and positive charges on the other, and it's going to repel. And every time it bounces off of the other conductor, it does the same thing. So you guys can see it moving as I bring it close, pull it away. It's going to keep bouncing. Put a little more charge on it. And it's going to keep going. So I could just continue the cycle. And it's going to keep taking charge. Well, I'll show you that in a second. It's going to keep taking charge from the balloon ultimately.
He's lying, there's a motor in the wood.
There's a motor in the wood. But yeah, so that's how this works. It is called the Franklin bell. Very good. Yeah, so like I said, as I move it closer, the electric field shows up and it begins rearranging the charges in the conductor. That rearranging, oh, and then I got it spinning, so I lost it. I guess after a while, I ended up losing it from that. But anyways, you guys have seen it by now. Hopefully you guys understand what the crazy. You discover physics is all a lie. It's not a lie, I swear. So what's actually happening here? Can we use our knowledge of conductors to understand what's going on with this Franklin bell? And we sure can. If you have the one conductor here, let's just do circles here. If you have the one conductor here, the other conductor here, and then something in the middle, well, if you introduce charges, and we're just going to pick negative charges for the sake of simplicity. So now we're going to have a bunch of negative charges that have an electric field going this way. Now opposites are going to attract, so you can imagine that a bunch of positive charges will show up on the surface of the conductor. Okay, why? Because there's an electric field, again, trying to go this way. To get to these negative, it's from the negative charges. There's a field going this way. So of course, all of the positive charges are going to ride that electric field to be attracted to these negative charges. So that means there's going to be an excess of negative charges that are going to show up over here. So again, now inside of the conductor, you get just enough electric field to cancel it out so that there's zero electric field in the center. But now you have negative charges here. So what's going to happen here? Positive charges, okay? Negative, positive, negative. So now, when this ball starts swinging, it gets close enough to here where these charges start to mix. And you get an excess of negative charges on this side, okay? What happens then is, this is still the same. So this wants to be the same to match with this. So more electrons are going to shift here. So now you're going to have a net negative here, and you're going to have some negative charges there. So these two are going to end up repelling each other. So it comes and it bounces and then repels itself away. Then it does the same thing. It comes out here, and now we're going to end up getting a bunch of negatives here that are going to want to hit the positives here. They're going to touch, again, mixed charges, and now there's going to be an excess, and it's going to reflect back that way. And it's going to keep doing this back and forth, and every time it does this, then every time it bounces the surface, it's going to hit and take the charges all the way until this ends up dissipating away to the air or whatnot, or used. So that field, and I admit there are gnomes moving it around. So there are, in fact, no gnomes. Let me see if I can give you another demonstration from a wider angle here. So again, I'm just rubbing the balloon on my hair. That's it. I'm going to get this in motion, putting it close, pulling it away, putting it close, pulling it away, putting it close, pulling it away, putting it close, away. So just you can see how it goes, and that's all it is really. Okay. Demonstrations, yay! We like physics, and physics likes us. So now you all know how.
Oh my God! I can see you are wearing a wig now.
I wasn't wearing a wig. I'm gonna put my cardigan back on. Can you prove? All right, very good. I can neither prove. Triboelective effect. Yeah, that's the thing that's doing. So this is really, really related to the Van de Graaff generator that we're making on Sundays, right? Like that's all what this is, right? Static. It's electrostatics. We're ripping the electrons off of the PVC, and we're implanting them onto the surface of a conductor. And then that conductor is charged, and then you can check yourself, and it's cool, and you make friends. So now let's talk. So that's where the induced charges come from. The induced charges, again, are these charges that come to the surface to cancel away the electric field, and then as they're moving around, because they can go back and forth from the conductor to conductor, and then of course you get an excess of charges somewhere, and then there's repulsion, and that's what powers the Franklin bell back and forth. Okay, so that's induced charges. Now, if you're on the notes, I left a little space for writing if you wanted to write anything down from that little demonstration. Make a giant Van de Graaff, see if you can make x-rays. Danger. Okay, so we're almost done. We got like a little bit less than a page and a half. So if we want to, let's talk about a few of the consequences of these surface charges, of these induced charges. The E field outside the conductor, of course, is perpendicular to the conductor, and it's going to be sigma epsilon naught times n hat. That's just, specifically we're talking about a sheet of, I should have specified the shape. So let's talk about a sheet. Actually, this might be true always, actually, now that I think about it. But for the sake of example, let's say we're going to talk about a infinite surface charge. And we also know in terms of potential that sigma is equal to the epsilon naught dv dn, where n is the normal vector. Let's keep moving. And in terms of potential, we have this. And then what do we make of the forces from the charges on the surface? And the forces are a little bit different, so let's do a little bit of investigating those. And really, it turns out that it's the electric field of the average times the charge density. How do we get this? Which was really, especially for the surface charge of an infinite plane, it's going to be 1/2 times sigma of the electric field above plus the electric field below. Now, that might not seem necessarily intuitive, so let's talk about that. If we take a source of a patch, we'll call a patch of this structure. We'll call it EP for E patch. Okay. Now, if we want to talk about the electric field of the whole top or the whole above, right? Then we could say the electric field of the above is just going to be equal to. What do we got? Bits study. Thank you for the follow. Welcome. E above is going to equal E other, which is just everything on the outside of the patch, plus EP, the electric field from the patch. Acting as some kind of conductor, you have to ground. So I have to ground this one. That's why you saw me touching it. When I touch it, I'm grounding it so that the charges flow through it, so that you don't end up with excess charges on this one, because you could easily end up with excess charges on that one, but since I'm grounding it, all of the excess charges are exiting through my body, so that every time this one leaves, this neutralizes again, so that when it comes back and touches it, it's it's transferring, charges, and then I'm actually taking them back by grounding myself. That's the point of touching it. Yeah, if you don't touch it, it won't work. Now, if we take the electric field from the bottom, it's the same thing. It's the electric field from everything else minus the electric field from the patch. Now, here's the deal. What if we say we want to talk about the entire contribution of the electric field from both the top and the bottom? Well, superposition tells us we can just add these, okay? And then we're going to actually figure out...
You are not well grounded.
Well, true, yeah. I mean, maybe it would work better if I was well grounded. I thought about it where I earlier today when I was doing it, I put a metal band on my arm and just a wire on my arm and then connected to the ground and everything like that. But it is just, I could make it, I did enough times this morning where it worked without it. So I just felt like doing that. So we can then add those two equations. So we're going to get E plus A plus 2 times the electric field of other, which is both the top and the bottom of the other, right? That's the rest of the electric field. And then the patches will subtract away. So if we wanted to say, what was the electric field of everything else besides the two patches from top and bottom? Well, that's simply just going to be the average. It's going to be 1/2 times the E above plus E below. Okay? So really what we're saying, we're talking about force. Force is an interaction between two objects, and what are those two objects? Well, for this specific case is how much force is acting on any patch from out here, the other, right? How much force is acting on that patch. So the force, then we could also say the opposite direction, how much from any patch is acting on the rest of the charge density, and we could just give this form, which is really just the opposite. It's like, it's how much, force does this whole thing feel from any patch. And then I think this is nice. We do this on purpose, so we'll call this the electrostatic force. Static force. And then, of course, if we have a force, we can talk about electrostatic pressure, which is just going to be epsilon naught divided by 2 times E squared. Okay? And this simply just comes from taking, force, which is pressure times area, and then, working that out. Pressure. No pressure. Well, no electrostatic pressure. Okay, so last but not least, we're going to talk about capacitors. This is the last section of the chapter. We're not going to be doing any examples today. If you guys would like to do some examples, please let me know, and we'll dedicate some time next week to doing some examples from chapter 2. Not necessarily homework problems, but not opposed to it, I guess. And if you just had some two wonky shapes, right? So we're going to say this is plus Q, and we're going to have another wonky shape, and we're going to say this is minus Q. And we're going to say, okay, so now we have two conductors with opposite charge, plus and minus Q. Let's talk about them. What is some things that are happening with this arrangement? So let's talk about the potential first. The potential is going to be V plus minus V minus, okay? Potential from each of them, right? And we're just taking the potential difference from them both. And we get the integral over the electric field dot dl. And we'll say from plus to minus. Okay, the distance really. Now, if the shapes are complicated, finding the E field is going to be a mess, right? How are you going to find the E field from these when you have these really obscure shapes and we can't do something simple like Gauss's law? Well, we don't necessarily need the E field. All we need to know is that the E field is proportional to the charge. Right? The actual E field can be given by 1 over 4 pi epsilon naught times the integral, times the integral of rho divided by crazy R squared times crazy R hat d tau. We did this a lot early on, like in discussion sections 1 and 2. Right? So now, if we know that it's proportional, like we would double Q, we'll double E. Or double P will, or double rho, will double E. And likewise, and I think that the idea is how do we know that the charges are distributed evenly, and I think that's something we have to take for granted right now. And Griffiths says we'll talk about a lot more about where that gets distributed in chapter 2. The surface, it's a boundary condition problem, so we'll talk about that in chapter 3, Chapter 3 we'll talk about that. But for now, just imagine that that this is true always, okay? And those are proportional, and E is proportional to Q. So therefore, Q is proportional to to V, right? Because E and V are just a divergence away, or an integral away. So now, how are they proportional? They're proportional by some constant. What is that constant? It's capacitance. Yes, capacitance is the constant. You could think of it as the constant that is the proportionality between the charge and potential, okay? Now, of course, we can change that constant, so, how much is it really constant? But let's talk about, for electrostatics, we're not really worried about it too much. We can charge up a capacitor to a certain thing, right? Certain voltage, potential. But what are we doing by charging it? And what we're actually doing is we're building an E field. If we have, a capacitor, we'll do a parallel plate capacitor because they look clean. If we have a parallel plate capacitor, we're adding charges to this. You could add them one at a time if you wanted. And every time we do that, there's more electric field showing up here. And what exists in electric field? Energy. So you're adding energy to the system by adding charges to the surface and building up an electric field inside this system, okay? Now, if we were to rewrite the voltage as equal to the work divided by the charge. Remember, at the very, very beginning, I said our simple understanding of work is that you have this, right? You have the charge times some potential where the potential is associated with another charge, okay? That's the energy, the work, stored inside the capacitor. So you can imagine that if you charge it up to a certain Q, you would have this much potential and that much work in order to do that. So how do we get up to that work? Well, let's consider dQ, or excuse me, dW, because remember, we're talking about adding infinitesimally small amounts of charge at a time, okay? And we're just going to integrate that now, integrate both sides. And we know that if we integrate this from 0 to Q and 0 to the total work, then what we'll get is work is equal to Q squared, well, excuse me, 1/2 Q squared over C. Okay? Right, this is just Q, so we're integrating it once, so we get Q squared over 2, and there's a 1 over C in there. Straightforward integration. So then this is then, of course, equal to 1/2. So we want to substitute this Q in for this. We get 1/2 CV squared. Okay? So our work is equal to 1/2 CV squared, where V is the final potential of the capacitor fully charged. So that's it for chapter 2 of Griffiths. We figured out work and how it's associated with building up an electric field inside of a capacitor. And that's it. How did we do? Oh, this was kind of a short lesson today. I didn't realize it was so short. We probably could have gotten away with doing an example. I think I was a little bit concerned that I'm going to get my coffee rolling here. If you're going to have some coffee with me, now's the time. Have a cup of Joe with me.